We've experienced two types of systems of linear equations so far. The first one here is the situation where we have no solutions. No solutions. And in two dimensions, that means that the lines are parallel. We have parallel lines. In three dimensions, that meant that we had parallel planes, that they did not have any intersection points. We're going to focus just on sort of the 2D analogy here and think about how this extends to multiple dimensions. Here we have one solution, and that one solution means that the lines aren't parallel and they share a single common point of intersection. In three dimensions, we saw three planes that all intersected one another, and there was one point that they all shared in common. And now we're going to consider the third possibility, where there are infinitely many solutions. And you might look at this graph right here and think, well, you've only plotted one line. And that is true. And at the same time, there are actually two lines here. It's going to be hard to see, but there's a black dotted line right on top of the blue line. And this is actually the system x plus y equals 10 and 2x plus 2y equals 20. Now in the second equation, if you notice that we can divide both sides by 2, if we divide both sides by 2, we get x plus y equals 10 for our first equation, and 2 cancels here, and then we get 10 on the right. So actually, these are exactly the same equation. They're just a little more disguised, and it's not something that we may notice all at once. Now, in three dimensions, this is going to be where planes intersect in more than one spot, but we'll come back to that. So the points that work for the first equation are identical to the points that work for the second equation. So if we analyze just either of the equations, we see that both of them are the graph of the line y equals negative x plus 10. And right away, we could probably point out a number of different solutions. It just depends on what value of x and what value of y we choose. So if we created a little t-chart and just chose some values of x, well, x can take on any value, positive, negative, or 0. So maybe we put a 0 here and say, well, if x is 0, and 0 plus 10 means that y is going to be 10. X could be positive. For example, we could plug 5 in for x, and we get negative 5 plus 10 is positive 5. We could plug in 7 if we wanted to, and that would give us a y value of 3. And we could also go in the opposite direction. We could plug in a negative 2 for x, and negative 2 is positive 2 plus 10 is 12. And we could pick, say, negative 6.1 if we wanted to, and that would give us a y value of 16.1. So we see that we can go on and on with this table. There's really no limit of x's that we can plug in. So we see that there are going to be infinitely many points. We could actually mark them and mark any points in between the points that we're drawing. There are infinitely many points just in any finite strip. So how do we begin analyzing this? Well, we could look at this and say, if you give me a value of x, given a value of x, say we hold x constant, and we'll just say x equals c. Now all that means is that we're assigning a value to x, we're just not specifying what that value is. This is called a free variable. We'll write that down. X is a free variable. And what we mean by free variable, it means that you can pick any value, you can assign any value you want to it. It's free to be whatever we would like it to be. Well, in that case, if x is equal to c, then y is going to be the negative of x, negative c, plus 10. So our solution set would be all ordered pairs of the form x comma y equals, well, for x we said we're gonna assign it a value, and then whatever value we assign to x, y is going to be the negative of that value plus 10 more. So any point of this form will be on that line. So for instance, if we say c is 0, then negative 0 plus 10 is 10, and that's that point right there. If we pick c equals c is 5, then we get the point 5 comma 5, which is this point right here. And this is a way of describing that solution set when there are infinitely many solutions. Okay, that's really all there is to it. It seems like a very abstract notion, but all we're doing here is we're saying, well, pick a value, and then once you've picked a value for x, then y will be determined based upon that. So once again, when we use notation like this where we are assigning a value, a constant, a known value to x, we're just not writing out what that constant is, because that constant could be, any one of these infinitely many values of x. So when things are not so apparent, how do we go about doing this? Well, first of all, let's take a peek at our equation and put this into an augmented matrix: 1, 1, 10, 2, 2, 20. Produce the reduced row echelon form, because this is where we're going to make our judgment of the solution set. This is just how we are doing it, since it's very efficient, and most equations will not present themselves as, most systems won't present themselves as having infinitely many solutions. So if we put this in, create a new matrix, 2 rows, 3 columns, we have 1, 1, 10, and we have 2, 2, 20. Define that. Produce the reduced row echelon form of A, and we get 1, 1, 10, 0, 0, 0. Well, what happened to that second row? Notice that it isn't 0 equals 1, it's 0, 0, 0, which we're going to write down in a moment and see that that's a completely valid statement right there. It just says that 0x plus 0y equals 0, which means 0 equals 0, which is always a true statement. And if we think about the Gaussian elimination that was performed, if we think about how we have gone about this, then our first task is to make this first one right here, or this first value, a pivot of 1, which it already is. And then to cancel out this 2 to make it a 0, we would take negative 2 times the first row, add it to the second row. Negative 2 times 1 plus 2 is 0. Negative 2 times 1 plus 2 is 0, and negative 2 times 10 is negative 20, plus 20 is 0. So we can see mathematically that in one step, we're done. We can't get this component right here, second row, second column, we can't get that to become a 1 because there's nothing we can scale this row by to make a 0 into a 1. So we get 1, 1, 10, which notice is just the first equation in this case, and 0, 0, 0. So coefficients of x, coefficients of y equals constant. And so this reads 1x plus 1y equals 10. And the second equation reads 0x plus 0y equals 0, which is the statement 0 equals 0, and that is always true. So when you see something like this happen, and you don't get 0 equals 1, that's usually going to be indicative of there being infinitely many solutions. Now, the way to tell is to read all of the lines, to read all of the equations and write them out, because in some cases there could still be a unique solution if there were, say, 3 equations and 2 variables and only one of them is a multiple of the other, then you may still get a distinct solution, and this is why it's always important to write things out. Now, when something like this happens, we see that the only requirement, I'm going to write this as the requirement of the solution. Well, 0 equals 0 is always true, so there's no problem with that. The requirement is that the sum of x and y is 10. That's the only requirement. It doesn't tell me what y equals. It doesn't tell me what x equals. It just says you can have any solution as long as the sum of their two values is 10. Okay, well at this point we can go a number of different ways. We could say that as long as you pick a value for one of the variables, the other will be determined. Okay, meaning that if I put in a y value of 6, then that would mean that x has to equal 4, right? That x is determined fully by the value of y that you give it. Now, here we said that assign x to be a value just because that's the way we're used to writing equations. We say plug in a value of x, give me the value of y. But usually when we get infinitely many solutions like this, what we do is to make this a very efficient process, even though it might seem kind of unnatural at first, is look at the first row and identify where the first non-zero value is. Well, that's in the first column. That's this number here. Make that variable not be the free variable. You might say, but Milos, up here you told me that x is a free variable. Well, yes, based on how we chose, but we could also argue that y is a free variable. It doesn't matter. One of them is free to vary is the bottom line. If you make one of them free, the other one is determined by whatever first assignment you make. Now in the second, we kind of keep doing this going row by row. In the second row, we look for the first non-zero value. Well, we check this is 0, we check this, that's 0, and we've run out of variables. So any variables that do not have a 1 in their column will be considered as the first non-zero value in their column. This has a 1 obviously, but there is no row in which y corresponds to the first non-zero value. Therefore, whatever variable is left, we will consider to be the free variable. This just makes it the same process every time. We'll see that in the next example a little more clearly. Okay, so what we do at this point is we say, let y be the free variable. Okay, so let's just go with this for a second. Y equals c. So assign y to be the value of, to be a constant value. And at that point, if y is assigned to be a constant, that means that x plus whatever we plugged in for y has to equal 10. And that means that x would have to equal 10 minus that constant. Now, we get the solution set. We're going to keep going with it. We're going to see how these connect. The solution set, based on how we just did this, will be x will be 10 minus c, and y will be the value c that we assign it. Now, this might look different, right? Because here we have c is the value of x, and negative c plus 10 is the value of y, which, by the way, 10 minus c is the same thing as negative c plus 10. Let's see how this works. So if I pick a value of y, let's pick a value of y in our table. If I let y be 5, then x has to be 10 minus 5, which is also 5. So notice that that same ordered pair right here is still a solution. Instead of fixing the value of x, we're fixing the value of y. Now also I could come up here and say, well, what if y is 12? If y is 12, then x has to be 10 minus 12, which is negative 2. And you see that we still generate the ordered pair -2, 12. It's kind of 6 of one, half a dozen of the other. It's the same thing. All right, let's take a look at another example. Now we're in 3 dimensions. And here we have the system of equations x plus y plus z equals 20, x equals 2z. We don't know how many solutions this will have just based on the appearance of these two equations, but we take a look at the graph and we can see that these are two planes that slice through each other, and notice that their intersection points fall along a continuum. Now, these planes go on forever, but it would be very hard to create a graphic that shows that, so we kind of just draw them as like sheets of paper. And this intersection point goes on forever because this plane right here keeps on going outwards forever, and so does this one here. And therefore, even along that short line, there are infinitely many points. Okay, so how are we going to see that? Let's set it up. 1, 1, 1, 20. Now, the second equation is not in the proper form. If I subtract 2z over and I write x plus 0y minus 2z, and then since I've subtracted that over, I have 0 on the right-hand side, helps me see the coefficients are 1, 0, -2, 0. Come back over to our utility here and set up a matrix with 4 columns, 2 rows. We have 1, 1, 1, 10. I'm sorry, 20. And then we have 1, 0, -2, 0. Okay, and now we're going to produce the Gaussian, we're going to conduct the Gaussian elimination on that matrix B. And we see that we get something interesting here. 1, 0, -2, 0. We get 1, 0, -2, 0. And we also get 0, 1, 3, 20. Not what we were expecting, but now if we take the time to carefully read back these equations, we have x, y, z, and our constants. And we see that in the first equation, we're saying that x minus 2z has to equal 0, which means that x has to equal 2z. Okay, we'll come back to this here in a moment, but that's a true statement. And also, we'll write down the second equation, which is y plus 3z equals 20. Okay, now as we look at this, the only requirements of a solution for this system is that the difference between x and 2z is 0, and that the sum between y and 3z is 20. If we want to think about what values we could assign to this, we realize that this doesn't tell us x has to equal blank and y has to equal blank and z has to equal some other value. However, one thing that we do notice is that in both of these equations, the value of x and y will depend upon the value that you plug in for z. Both equations have z in it. Both equations do not have x, nor do they both have y. So in this first equation, we're saying that x is fully determined by z. It's going to equal twice the value of z. And furthermore, we could say that y is going to equal 20 minus 3 times the value of z. So we see here that really z is the variable whose value we can freely assign. We're gonna make this statement right here. We're gonna say z is a free variable. Okay, now that required some extra cognitive work, but if we use our approach up here, where we kind of go row by row and identify the first non-zero value in each row and the corresponding variable for that column, then we can see that in the first row, if we identify where is the first non-zero value, oh, it's right there. That corresponds to the column for x. If I do the same thing in the next row, okay, where's my first non-zero value? That's 0. Oh, there's a 1, and that happens in the column corresponding to y. Now, we've run out of rows, and we do not have a row in which the coefficient of z is the first non-zero value. I mean, there are non-zero values for z, but they're not the first in their row. So that means that what we're going to do is we're going to identify z as the free variable. And notice that was the same conclusion we made here by analyzing these two solution equations and producing that conclusion. But here we did that very algorithmically. We didn't need to spend too much time thinking about the equations, although that's a good way to go. A lot of times we may have more than two equations and we really just want to get at the solution. Okay, so z is free. So what are we going to do? Well, we're going to assign, to be able to write out the solution set, we're going to assign to z some constant value. It could be 0, positive, negative. There's really no value that we can't plug in for z into these equations. And that's going to be true of linear equations in general. Okay, so now we know that x, in that case, if we plugged in c, some constant for the value of z, x would have to be 2 times that constant, and y would have to be 20 minus 3 times that constant. Therefore, our solution set will be all ordered triples. These are triplets, or triples. They're not pairs anymore. Pair means 2. Of the form, if we plug in c for z, then y will be 20 minus 3 times that value, and x will be twice that value. All right, let's look at an example, a possible solution here. Let's say that we pick z to be 2. Okay, if we picked z to be 2, we're just trying to produce one possible solution of that infinitely many solutions that we can pick. Z could be any value that we desire. That means that if we put in 2 for z, y will have to be 20 minus 3 times 2, or 20 minus 6, or 14. And x will have to be twice that value, which would be 4. So how do we know that this works? Well, we can come back to our system of equations. We have 4, 14, and 2. And let's see, 4 plus 14 is 18 plus 2 is 20, so that works. And we also need to make sure that x is twice the value of z. Well, if z is 2, then 2 times 2 is 4, and so 4 equals 4 is a true statement. And we can keep on going. We can pick different values for z. We could pick z equals -1. The point here is that we don't do this, that this is why we write the solution set like this in our final state. But we can keep on going indefinitely in this process. So you know what? We don't need to plug in z first. C is -1, so 2 times -1 is -2. 20 minus 3 times -1 is 23. And this value is -1. Notice that they sum to 20. -2 plus 23 plus -1 is 20. And 2 times -1 is equal to x. -2 equals -2. So that's another solution. And we can, again, keep on going indefinitely. And that's why we're taking this painstaking effort to write our solutions in this very general form.